Okay, so in this video, I'm going to give a small introduction to cryptographic hash functions, and I'll also explain one very important cryptographic hash function in little detail. So, what are hash functions? A cryptographic hash function is nothing but an algorithm that takes an input data of arbitrary size and produces a fixed size output of enciphered text, which we call a hash value or just a hash. This enciphered text could be anything, but generally and most commonly it is a password that we hash in order to generate the enciphered text, which is stored and later used to verify the user. This is one very common use of a hash function. So they're nothing but mathematical functions that can take an input data of any size. It could be a normal string, it could be a paragraph, or it could be the contents of a file, and accurate and generate a unique fixed size output for that entire whatever input is given. So it's able to map data of any size in order in n number of bits. So coming to some important properties of hash functions. These properties are must and required for any hash function to be a good hash function, and can also be used to differentiate two hash functions. The first is the non-reversibility property. It's also called the one-way function property. What this property is that any hash function should make it very hard for any attacker or perpetrator to try to reconstruct the original key from the hash value that is generated. So if any attacker could easily reverse engineer the hash function in order to generate the original key, it would compromise the security of the algorithm. So it should be non-reversible, or it should be very very hard to do that, or if not impossible. The second is the diffusion or avalanche effect. What this effect is that any small change in the key, like even changing one bit, like from 0 to 1, should result in a big change in the generated hash, and the hash should be completely different from when you didn't change. It's not like you change one bit 0 to 1, and again only one bit changes in the hash value. What is most efficient is where you change one bit in 0 to 1 in the original key, but the entire all the bits in the hash function change. That would be the best desirable feature. The third is determinism. What this is that ensures a one-to-one mapping between keys and hashes. So every key should only generate one unique hash, and there should not be two hashes for a single key. The opposite of this is collision resistance. What this is that one hash should not have two keys. So two keys should not be able to generate the same hash, because if they can, then both the keys can be treated as equal, and it exploits the collision property of hashes. And the last is the non-predictability. What this is that any hacker or perpetrator should not be able to directly predict the what the key could be from the hash value. So the hash value should be arbitrary and should be random. They should appear as they're random values, and should not be anyway related to the key that is thing. So it should not be something like a rhyming word, or you take the letters and jumble it, something like that. It should be a completely random generated hash. So some important features of hash functions. These features make hash functions very useful and are one of the most important reasons why we use hash functions. The first and the most important is the fixed length output. So the fact that a hash function can take data of any size and convert that into into a fixed length output, which is of n bits, is very useful in many scenarios. So the hash generator is much smaller than the input data and can be used to concise the data. And yeah, and is an n hash function with an n bit output is referred to as an n bit hash function. And most hash functions generate values between 160 and 512 bits, but mostly people stick to using powers of 2, which is 218 to 128, 258, 256, and 512. The second feature of the hash functions is efficiency of operation. So the hash function should be able to efficiently create the hash value for a key, but at the same time it should be very very hard to generate the same key from the hash function, if not impossible. And there should be one main difference between hash functions and encryption is that encryptions are two-way. So you have a text that you encrypt and create a cipher text, and when the person on the other side has to decrypt the text. So it's a two-way. You have to first encrypt it and then decrypt it. But hash functions are only one way. So you only have to encrypt the hash, and there's no way to decrypt it. You don't need to decrypt the hash function. All you can do is you can generate the same hash again in order to verify something. But there's no two-way process. You cannot decrypt the hash to get the original key back. So this is the main difference between hash functions and encryption. This is the example of the workflow. The message is passed into the hash function, which generates the value of fixed length. So coming to the design of hash functions, the action function is nothing but a mathematical algorithm that operates on two fixed size blocks of data in order to create one hash code. So this function performs the part of the hashing algorithm. Now, the size of each data block it really depends on what algorithm you use, and there are many different algorithms available nowadays. And typically, the size chosen for these blocks are 128 to 512. But again, people choose PowerSwift 2, which is 128, 256, 512. So the algorithm involves rounds of the hash function, and is very similar to like a encryption with block cipher. So each round takes an input of a fixed size, and typically a combination of the most recent message block and the output of the last round is chosen, and it performs the algorithm on that particular block and then moves to the next block. And this is repeated for as many rounds as specified in order to hash the entire message. And finally, the final output is the hash value. So the algorithm is a process of using the hash function to specify how the message will be broken up and how the results in the previous message blocks are chained together. So this is one of the main important features of the algorithm, and it also ensures that the avalanche effect takes place. So coming to the application of hash functions, the first important application is the password storage. So what the most common scenario, the most easiest scenario while storing a user credentials in a database is to store both the user ID and the password together. So when any request comes, you compare the user ID to the ID stored, and you compare the password to the password stored in the database, and then you can authenticate the user. But this poses a security risk where if any person, any attacker obtains the say the dump of SQL dump of the database, so now he can see all the passwords, and all the passwords are exposed. So he can easily get all the account credentials which can compromise the user's credentials. But what we can do to counter this is to hash the password and then store it in the database. So if we store the hashed password in the database, and only we know about the hash function that we use, what we can do is make sure that if any person obtains the SQL dump of the database, he can't do anything with the passwords, because he won't be able to know he won't be able to know what the passwords are, because the passwords are all hashed. And how we can actually authenticate is while the user sends a request with his identity and password, while checking, we check the ID with the ID stored in the database. But when we're checking the password, what we do is we hash the user password from the request and compare the two hashes, the hashed value of the password from the request and the hash value that we have present in the database. And if both the hashes are equal, then we can say that it's a legitimate user and we can authenticate him. So this way we can you perform the authentication while also keeping security of the user credentials and preventing any attacker from be able to compromise the credentials. The second application of hash functions are for data integrity checking. So in this scenario, for example, when you're sharing files over the internet, so if you're downloading a file from a site that's supposed to be something, there's no way that you can assure that that file is actually what it is. It could be malware, it could be a file made by some malicious person. So you don't the one way to in order to ensure that the file you downloaded is the right file and it has the right function is through hash functions. So the owner or the creator of the file can upload the file and also upload the hash value of the contents of the file, and he can upload that as well. And when the user downloads the file, he also can run the same hash function on the file he just downloaded, and he can compare the hash values of both what the owner said the hash should be and what hash he actually got. And if both are equal, then he knows that he has gotten the same file. If the values are different, they know that the file is a different file and that it could be a malicious file. So he could be aware of it and he could not run the application. So yeah, this is how it is. The original data, the hashing algorithm is hashed. The file is used parallel to the hashing algorithm, and it creates the hash value, and it sends the hash value through the network as well as the file, and the user will again hash the entire file and check the hash value. So one case study is the message digest algorithm. So the message digest family comprises of hash functions, and there are many different varieties of the algorithms: MD2, MD4, MD5, MD6, but they're all 128-bit hash functions. So these functions have been widely used in software world, and because they were very popular at one point of time, and because it was very secure as well at that point in time. So a lot of people used it for very variety of purposes. And one very common use of it is to compute the MD5 checksum for files, which is what I explained in the previous step, that you can compare the checksum of a file that you download. But one problem is that there are some insecurities identified in MD5. Like they found some researchers of a few years ago found that MD5 actually has collisions, but it would take a lot of time to actually achieve those collisions. So while it is a bad thing, it is very still it since it's very hard to actually get those collisions. MD5 is still used commonly nowadays, and it's still a viable option. But there are more algorithms which have come for after MD5, which have made it even harder to find collisions and made it better than MD5. So coming to the steps of how actually doing MD5, actually running the MD5 algorithm, the first step is to append padding bits. So what you do is you append extra bits to the original message. So if such that the length of the bits is congruent to 448 modulo 502. So which basically means that when you take the number of bits and modulo it with 502, the result you will get is 64. So that is how padding is done. And how what is suppose you've identified that you need to add 300 bits to the extra bits to the message. The first bit you add will always be 1, and after you add zeros. So you if you have there'll be 1 and then 299 zeros following your message. That is how padding is done. So appending length. So I can open this up and actually show how padding. Suppose you have a pad for 10 digits, and you have your value checksum here. This is the value of your message. So you have to add 10 padding. So what you do is you add 1 1, and then you add 9 zeros after it. So you get 10 values. And when you add 10 zeros, and when you take this entire thing and you do modulo 512, you will get 64. So that is how padding is done. So and after padding, you have to append the length. The next step is to append the length. So since we know after the padding that the resultant value is when you do modulo 502, you get 64 bits, which means that we still have a 64-bit capacity to add to the message, so that the entire message is exactly modulo 5. Is exactly divisible by 502. So we can add 64 more bits. So what we do in this step is we add a 64-bit representation of the length of the original message, right? And in case the message is greater than 64 bits, we only add the lower order 64 bits of the message. And then after that, the entire string that we have, entire message that we have will be a multiple of 512. So this is one online tool I found. So we can look at it. If I give the message hello world, and I convert this, as you can see, this is the ASCII value of it, and it says that my message contains 88 bits, which is right because there are 11 characters and each character is 1 byte, and 1 byte is 8 bits. So we have 88 bits, which means that we have to add 368 bits so that it becomes modulo 5. That it becomes 448 modulo 512. So if you add 360 to 88, we get 448, and when you do this mod 512, you'll get the answer as 64. So we need to add 360 bits. So what we do is we add 1 1, and then we add 359 zeros. And after that, we also add the 64-bit value, which is the length of the original message. And here the length of the original message is 88, so which is 101 1000, and all the rest are all zeros. So together, after adding everything, this becomes the resultant value of our padded and length appended string. And this is passed into the main main algorithm of the MD5. So coming to the main algorithm, after this, there's another small step, which is to initialize the MD buffer. So you create a 4-word buffer. Each word is predetermined, and these are constants that have to be used every single time in the algorithm, and these are stored in 32-bit registers. So you have the word A, word B, word C, and word D. So coming to the main algorithm, the main algorithm has 4 auxiliary functions. So each function performs a different purpose, and each function takes 3 32-bit words and produces a single 32-bit word as an output. So it is a way to map 32-bit words into one 32-bit word, and you create 4 as such mappings. So f of xy is x and y, or not of x and z, and similarly h of xy is basically x xor y xor z, which is nothing but the parity function. So you have 4 such functions which create unique mappings. And after that there is a table which is called the t table, and it's constructed from the sine function. And this is a 64-bit 64 value table, and each value has a unique each index has a unique value that is used as a reference in the algorithm. So this is the actual algorithm, the main part. So what you do is you have to initialize, you have to create a loop for I is equal to 0 to n divided by 16 minus 1. So you divide the entire message into 16-bit chunks, and after that what you do is that for you save the a b c d values, which were the constants we defined before. You start with a is equal to a, bb is equal to b, cc is equal to c, and dd is equal to d. And then there are 4 rounds. Each round you perform one function. The first round you perform the f function, the second one you perform the g function, third h, and fourth I. But you perform it on all the values at the same time. So in the round 1 we use this operation, which is a is equal to b plus for the representation a b c d k s I, we add b, and then you basically perform this operation right here, which basically generates a value for by calculating the 32-bit result for f of the f function, and we get a unique 16-bit value back. So you do the round one for all 16 operations, like in boxes, where each box follows the same format as this comment over here, a b c d k s I, and then you have to perform round 2 on the same thing, and then where round 2 uses the g function, and then you perform round 3, and then you perform round 4, and after that what you do is you have to append the value of a b b c c d d after all the rounds to a b c d, and then repeat the loop again for the next 16 word block. So as long as you can keep getting 16 word blocks in the message, you have to keep repeating this algorithm. And what at the end of it, what you get is a 128-bit hash. So after one round you get a 128-bit. So how it is each a b c d is 32 bits. So 432 is 128. So you have to append a, you have to you get the message digest output is produced as a b c d, where you just concatenate a b and c and d, and the low a is considered as a lower order, and d is considered as the higher order. So that way you can construct the 128-bit hash. So in every round you create the 128-bit hash, and as long as you can keep getting more and more 16 word blocks from the message, you keep changing the hash value function. But you basically you just keep modifying the 128-bit you already have, and in the initial 128-bit that you have is this 1201234567. So if the message is empty, the what hash value you'll get is nothing but 127 129 a b c d e f, and then the reverse of it. So you get a b c d, the default values is the hash value for an empty input. So yeah, even in the operations we use the t function, the t values uniquely. These have been predetermined from the sine function. That was the MD5 algorithm. A small example of we even looked at a small example of how to pad and all that. And that was the main. This is the main part of the algorithm. And the last topic is the problems with using hash functions. So hash functions are not perfect as they are, because it is still sometimes possible to crack the hash. People nowadays use what are known as rainbow tables, which are pre-computed hash functions for common strings and passwords. So in that case, it just becomes an O1 lookup. You get the hash value, and if the hash value already exists in the table, you have rainbow table, you can directly map it to a string. So if I have a rainbow table where I have values cat and dog, and I have cat mapped to #1, dog mapped to #2, and then I go and get the SQL dump of a table and see that the value of the password of one user1 is the same thing as the hash for cat. Then I know that his password is cat. I have gotten his password, therefore his identity is compromised. So that is one main problem with hash functions. So there are several ways to counter this. So yeah, that is one problem. Second problem is that attackers are equipped with fast hardware that can easily crack hash functions. So hash credentials, so they can basically run brute force algorithms on on high intensive GPUs and still be able to calculate. And not most hash algorithms are not completely collision resistant. So they have been known to contain collisions and produce same hash value for different credentials, but it would take a lot of tries to do it. And after that, yeah, those are the main problems with hash functions. So there are some common methods that you can do to in order to avoid these problems. The first one is called salting. In salting, you add random data to the plain text credential. Every single time you choose a predetermined salt, kind of like a small like a secret key, and every time you add that random data to the plain text before hashing it. So and now it becomes different hard for the attacker to decrypt the data, because he'll also have to unhash the hash value to get the original thing, because he has to also know the salt that you've used. And the second is the adaptive one-way function. And what this does is iterates on itself, and it feeds the output that is generated back as input in a manner that it causes it to ultimately take longer to execute. But this can be very useful to deter attackers from trying to brute force crack passwords, because every password will take a long time to the more number of tries you do, the longer it takes. So the first attempt can be very fast, but then it feeds the output back as input. So next time the input is even longer. So but it'll ignore the other part, the part of the input, but it will still take extra time. So every considered attempt, it takes more and more time. So this can be useful to deter hackers, because it will become a time waste for them. So one algorithm which uses this is the PBK DF2, which is password based key DF2, and also imported in libraries like Bcrypt is a very useful library for encryption and decryption. So that is all. That is a small introduction to cryptographic hash functions. Thank you, and yeah.